In this video, we're looking at line integrals, and we're starting with line integrals in the plane. So when we talk about line integrals, it's similar to a single integral, but instead of integrating it over an interval AB, we're going to integrate over a curve C. So instead of saying the integral from A to B of f of x dx, we're going to have the integral over C, and we'll have stuff here, and we're going to say the integral with respect to the space. So they're called line integrals, although curve integrals is probably a better terminology. They were invented in the early 19th century to solve problems involving fluid flow, forces, electricity, and magnetism. So when we look at this, we're going to start with a curve C given by parametric equations. We're going to let x equal x of t. We're going to let y equal y of t. And t is going to be defined between a and b. So you can see how that looks like a parametric equation. And once you have that, then you can see how we would be taking our sum of our spaces smaller and smaller as those p's get closer together. And so the definition of a line integral is given in terms of the limit, but here you can see how the line integral is an integration. And so we say the integral over the curve of f of x, y, ds is equal to the integral from a to b of the parametric equation f of x in terms of t, y in terms of t. And then you have the arc length we learned back in polar and parametric equations. So we have the square root of dx over dt squared plus dy over dt squared. So this integral is not hard. You just have to use it in terms of parametric equations. And we're going to find that we don't always use t as our variable. Sometimes we use x, sometimes we do other things. Before I do an example, there's two things I want to point out. That first of all, the value of the line integral doesn't depend on the parametrization of the curve, as long as the curve is traversed exactly once as t increases from a to b. So notice that we're going to travel the curve exactly once. And secondly, when we take this curve, we're going to take the c and we're going to put that in terms of the bounds of t. So c is going to be the curve, and since we're working in parametric, we're going to say t is between a and b, which we wrote up above. And then this function of xy turns into the other because it's the function of xy in terms of t. And then ds is what we learned back in the arc length and the parametrization in polar. The parametrics in polar, so we have dx over dt squared plus dy over dt quantity squared. So this formula hasn't changed since chapter 10. It's the same formula. So life is good. So you can see how all of this fits together. This example says to evaluate the integral over the curve c of 2 plus x squared y with respect to the space, where c is the upper half of the unit circle, x squared plus y squared equals 1. So if you think about the fact that we're putting it in terms of parametric, this leans into polar. So remember that a circle, this is a note you need to make if you don't know it, but remember the circle is x equals r cosine theta, or t, x equals r cosine t, and y equals r sine t. So that gives you a circle. And anytime you're looking at a circle, you're going to go ahead and use those. So we're going to say the r here, the radius of that circle is 1. So we're going to use x equals cosine of t and y equals sine of t. So that means for our formula, we need dx over dt equals negative sine of t, and dy over dt equals cosine of t. So now we're going to take this equation that we have. We have the integral over c. So we're going to say the equation is 2 plus x squared y. Now x is cosine, so we have cosine squared t, and y is sine t. So this is our f of x of t, comma y of t. So we substituted the parametric equation here. And then we have the square root of negative sine t quantity squared plus cosine of t quantity squared with respect to t. Now we need to talk about bounds. We're on the upper half of the circle. So when you think about the upper half of the circle, this means that t is going to be between 0 and pi, because think about your unit circle. So we can say that the bounds on this are between 0 and pi. So we're going to say the integral from 0 to pi, we have 2 plus cosine squared t sine t, the square root of sine squared t plus cosine squared t dt. So we have the integral from 0 to pi. We have 2 plus cosine squared t sine t. Now, the square root of sine squared plus cosine squared plus cosine squared is 1, and the square root of that is 1, so we're just going to put dt, because this becomes the number 1. Now, this isn't too bad. We're going to use u sub, so I'm going to split the integral into 0 to pi 2 dt, plus the integral from 0 to pi cosine squared t sine t dt. So let's let u equal cosine t, because that's where our power is. Then du is negative sine t. So that means we're missing a negative on here. So let's put our negative out front, the integral from 0 to pi. But since we're doing u sub, let's change our bounds. So when x equals pi, u equals cosine of pi is negative 1. And when x equals 0, cosine of 0 is positive 1. Not u, but t. So we're going to say there's a negative now, and we have the integral from 1 to negative 1. Some people like to switch that. I just take it like it is. So we have u squared du. When we integrate u squared du, when you integrate with respect to u, you should get a u answer from negative 1 to 1. So we have negative 1/3 parentheses 1 plus 1/3 minus 1. Let's go ahead and do the 2. So let's finish it. So we have negative 1/3 minus 1/3 makes minus 2/3 here. Now let's do the first part. So when we integrate 2 with respect to t, we get 2t from 0 to pi. So we have 2 pi minus 0. So we have 2 pi for this part. So our answer is 2 pi minus 2/3. And that is the length of the space 2 plus xy bounded by the upper half of the circle. Now this part makes sense, but suppose you have a piecewise smooth curve where C is a union of finite smooth curves here, like the figure below. So you can see you have a line segment for C1 and a curve for C2 and a line segment for C3 and a curve for C4 and a line segment for C5. So you would find the integrals separately for each piece and then add them together to find the total line integral. I told you it makes sense. All right, so let's look at one. Evaluate the integral of 2x ds over the curve, where C consists of the arc C1 of the parabola y equals x squared from 0 to 1, 1, 1. So here we have y equals x squared here. And this is the point 1, 1. And then we followed by the vertical line segment C2 from 1, 1 to 1, 2. So here we're going to 1, 2. And this is the equation x equals 1 when you think about that. So when we look at it, we need to put it in terms of a parametric equation. In this case, we're going to let x be our parameter. If you make that decision at the beginning, just remember to live with it, to live in it. So let xe be the parameter. Let's look at our first equation. Let's call it C1. So for C1, we're going to let x be the parameter, so x is x, and y is x squared, and notice that our x is bounded between 0 and 1. So let's go ahead and do that part, and we're going to integrate. We have 2x, so that stays 2x, and we have the square root of the derivative of x with respect to x is 1 squared, plus the derivative of y with respect to x is 2x quantity squared, and we're integrating with respect to x from 0 to 1. So we have the integral of 2x from 0 to 1. Let's make sure that looks like a 0. And we have the square root of 1 plus 4x squared dx. So let's use u sub. Let's let u equal 4x, 1 plus 4x squared. All right, 4x squared plus 1, because apparently I was on a roll there. And du then is 8x dx. So dx is 1 over 8x du. U sub is a skill. You need to make sure you've got this. And when x equals 1, u equals 4 plus 1 is 5. And when x equals 0, then u equals 1. So we're going to say the integral from 1 to 5. And we have 2x square root of u times 1 over 8x du. So those x's cancel beautifully. So we have the integral from 1 to 5. 2 over 8 is 1/4, and I'm going to put that out front. And we have u to the 1/2 du. So this means we have 1/4 times, this becomes u to the 3/2. So the coefficient is 2/3 from 1 to 5. So 1/4 times 2/3, I'm sorry, 1/4 times 2/3 is 2 over 12, which is 1 over 6. And then I have 5 to the 3/2, which is 5 squared of 5, minus 1 squared of 1 is 1. So that gives us C1. And now let's go talk about C2. When we look at C2, I'm going to come here where we can see the graph. So let's look at C2. And as we look at C2, we're going to let y be the parameter because we have x equals 1 here. So we're going to let x equal 1. We're going to, let's say, let y be the parameter. I'm going to leave off the word the for space purposes. So let y be the parameter. X equals 1, so y equals y. And your y values are bounded between between 1 and 2. So that means we can write the integral from 1 to 2. And the original problem says 2x. So we're going to say 2 times x is 1. The square root of the derivative of x with respect to y is 0 squared, plus the derivative of y with respect to y is 1 squared, and we're working in terms of y. So this is not a bad integral at all. So we have 2, and the square root of 1 is 1 dy. I'm going to go ahead and rewrite it because you should never integrate something that looks like that. So leave it off if you'd like. Now when you integrate 2 with respect to y, you get y from 1 to 2. So we get 2 times 2 minus 1, which is equal to 2. So that means our total line integral is 2 plus 1/6 times 5 square root of 5 minus 1. And you should always combine like terms. So we have 2 plus 5 over 6 square root of 5 minus 1 over 6. So 2 minus 1 over 6 is 11 over 6 minus 5 over 6 square root of 5. All right, so the piecewise functions aren't too bad. It's just doing them in pieces and paying attention to which parameter is going to work best for you. A wire is bent into the shape of a semicircle x squared plus y squared equals 25, where x is greater than or equal to 0. If the linear density is a constant k, now remember that's your rho, so rho is equal to k. Find the mass in the center of mass of the wire. We remember that the mass is equal to the integral, the double integral over the space d of rho of xy with respect to the area. So we're going to look at it in that way, but in this case, rho is a constant k, so that makes it nice and easy for us. So we're going to work with it in terms of our curve, because our bounds are not in terms of x and y, our bounds are in terms of a curve. So we're going to move this into here and say rho of xy with respect to s. So we're making this change. Now when we look at this change, our rho is just the constant k, and then we need to define our variables. So I shouldn't start with that. So let's draw a line through this and let's come back to it. Our parametrization, we have x squared plus y squared equals 25. So we know that that's a circle. So we can say x equals, our radius is 5 cosine theta t let's call it t, and y equals 5 sine t. And x is greater than or equal to 0. That means that we're on the right side of the graph, so our bounds for t are negative pi over 2 to positive pi over 2. Now we can go back and do our moment. So our moment is the integral from negative pi over 2 to positive pi over 2. And our rho is a constant k. And then we have the square root of, the derivative of x is negative 5 sine t quantity squared. And the derivative with respect to y is 5 cosine t quantity squared. And then we're integrating with respect to t. So these are going to get to be old hat, but when you write math, you write it for your classmates to read, so you have to write more math than you really want to. So negative 5 sine t squared is 25 sine squared t. Don't just jump straight in, you got to put some notes in. And when you square the 5 cosine t, you get 25 cosine squared t dt. I'm going to write one more line in there. Remember, your average Calc 3 student should be able to read your work. So we have the square root of 25 times sine squared t plus cosine squared t. I think that you could skip this line, probably. I will let you, we're good. dt. Now the square root of negative pi over 2, make sure it looks like a negative to a positive. So we have k, and the square root of 25 is 5. And the sine squared plus cosine squared is 1, so we just have 5 times k. So when we integrate with respect to t, we get 5t, 5kt. Remember, k is a constant from negative pi over 2 to positive pi over 2. So then we have 5k times pi over 2 minus a negative becomes a plus pi over 2. So we have 5 pi k. So that is our moment, right? That is our mass. That is our mass, so that's a good plan right there. Now we also have to find our center of mass. So if you go back and look up those formulas, we say that x bar is equal to 1 over m times the double integral of x times rho in terms of xy with respect to the area over the region D. So we're going to transform this to say x bar equals 1 over the mass times the integral over the curve, and we have x times our rho is k with respect to s. So then we can say 1 over 5 pi k times the integral from negative pi over 2 to positive pi over 2, and x is equal to 5 cosine t times k times the square root of, it's a long square root, so maybe I'll write small. We're going back to negative 5 sine t quantity squared is 25 sine squared t plus 25 cosine squared t, all with respect to t. Now this is the same as it was before, so if you want to do it off to the side and bring it in, or just say from above, that works too. So I just wanted you to see where it came from, at least this once. So we have negative pi over 2 to positive pi over 2. And x is 5 cosine t times k. So 5 cosine t times k times the square root of 20. We factor out the 25. We know this equals 5 from above, so I'm just going to put a 5 here. So we have 1 over 5 pi k, and the 5's and the k's are both constants, so they're going to cancel. I'm going to leave the k because I already wrote it. So we have negative pi over 2 to positive pi over 2. So we have 25k cosine t dt. Now the k's cancel and the 25's are going to cancel as well. So we bring the 25 out. We have 5 over pi, the integral from negative pi over 2 to positive pi over 2. And we're integrating cosine of t dt. Not a bad integral. When you integrate cosine, you get sine of t from negative pi over 2 to positive pi over 2. So we have 5 pi when you evaluate sine of pi over 2, it's 1. Minus when you evaluate sine of negative pi over 2, it's negative 1. So this becomes 2. So we have 10 over pi. And this is our x value for our center of mass. Now we're going to find the y value. So we're going to say y bar is equal to 1 over m times the integral over c of y times rho xy over with the integral over the space. So using what we have above, we're going to say m is 5 pi k. We have the integral from negative pi over 2 to positive pi over 2. And y is 5 times sine of t. And the rho is k. And we know that the square root of all that mess is 5. And we're going to say with respect to t. Now the k's cancel and the 5's cancel. So we're going to bring that 5 out to be 5 over pi. And we have the integral from negative pi over 2 to positive pi over 2. And we're integrating sine of t with respect to t. So when we integrate sine of t, we get 5 over pi. And the integral of sine of t is negative cosine of t from negative pi over 2 to positive pi over 2. So we have negative 5 over pi. And cosine of pi over 2 is 0. Minus cosine of negative pi over 2 is 0. So this equals 0. So our y value for our point is 0. So to answer the questions, our mass is 5 pi k, and our center of mass happens at the point 10 over pi, comma 0. So it's not too bad. It just brings in what you've done and ties it into the concept of line integrals. So it's kind of cool. Two other types of line integrals are obtained by changing your ds. You can use dx or dy. So here we're looking at line integrals with respect to x or y. And it's sometimes called a line integral with respect to arc length. So here are the two formulas given. Notice that you still have your function here, but we have x prime of t dt. But if you think about the fact that we're in terms of the x, the square root of x prime squared is x prime, so that makes sense. So in terms of x or y, that means it would become these two equations. Now, often you'll see line integrals with respect to x and y at the same time, so it's common to write them together. So we say that the integral with respect to x plus the integral with respect to y, and you can write them in the same integral, or you can keep them separately. So it's interesting that the integral over c is going to be the same. There's one more reminder in here that I would like to bring out. And when you're setting up a line integral, sometimes it's hard to think of a parametric equation for a curve whose geometric description is given, which is true. So like x squared plus y squared is always x equals r cosine t and y equals r sine of t. So when you're thinking about a line segment, it's sometimes hard to put that in parametrics. So remember the stuff we learned back in chapter 12. The r of t is equal to 1 minus t times r sub 0 plus t r sub 1, and t is between 0 and 1. So that'll help you with your line segments, and we've worked with it since then. So let's go ahead and look at an example here. Now this problem says to evaluate over c y squared dx plus x dy for two different paths of c. So we're going to use the integral with respect to x or y that we looked at up above to do this problem. So let's start with the parameterization of, we have a line segment. Now when you look at this line segment, we're going to start over here, and we need the parameterization for this line segment C1. So we're going to say x equals, now notice the slope of this line is m equals 5. So we're going to say x equals the slope, which is 5 times t, minus that x value is 5. And the y is equal to slope is 5t minus the y value of -3. Now you can use that equation that I gave you in the previous screen. If you do r sub o, your starting is that vector right there. So r sub o is the vector -5, -3, and r sub 1 is the vector 0, 2. But when we built these earlier in Calc 3, we went with the slope and one of the values to build it. So you can go either way as long as you build it. It's good. There's lots of ways to get there. Life is good. Before we move on, they give us the bounds for t if we do it this way, r0 to 1. If we find our bounds for t on the yellow, we should be able to see that they are yellow to 1. They are yellow. In the yellow, they are 0 to 1 for t as well. So we are given the integral over c of y squared dx plus x dy. Now this integral applies to the whole thing. They don't use parentheses. That's not standard notation there because this gets very complicated with lots of parentheses. So we're going to say the integral from 0 to 1. Now y squared means I have 5t minus 3 quantity squared. And dx means we're finding the derivative of x with respect to t. And that would be 5 dt plus. Now let's talk about the x part. So the x part is 5t minus 5. And dy means the derivative of y with respect to t. So that's 5 dt. Think about it this way. dy equals 5 dt. And above that, dx also equals 5 dt. So that's what goes in place of dx and dy. So we put 5 dt for both because they happen to match, not from any other crazy reason, but we take the differential of both sides, and that's where that comes from. So we do the integral from 0 to 1, and notice we have a 5 in both of the above terms. So I'm going to take this 5 out of here and this 5 out of here, and I'm going to put it out front. So I have a 5 here. And then we have 5t minus 3 quantity squared. So that's 25t squared, and 5 times 3 is 15. Doubled is minus 30t plus 9 with respect to t. Plus, here we have 5t minus 5 with respect to t. All right, so let's combine like terms. Please don't integrate like that. Go ahead and combine like terms. Notice they're all with respect to t. So we have 25t squared, and we have minus 30 plus 5 makes minus 25t, and we have plus 9 minus 5 makes plus 4 with respect to t. So we have 5, and let's go ahead and integrate to be 25 over 3, t to the third, minus 25 over 2, t squared, plus 4t from 0 to 1. So when we put in 0, that's nice, but when we put in 1, we have 25 over 3, minus 25 over 2, plus 4, minus 0. Let's go ahead and write that. And this means I have 5 times negative 1 over 6, which is negative 5 over 6. And that's our answer for C1. So now we're going to look at C2. C2 is the arc of the parabola. So let's pull the picture back in so that we can kind of see that happening. If you go back and look at C2, it says C2 is the arc of the parabola. X equals 4 minus y squared. And we're looking at the same endpoints from negative 5, 3 to 0, 2. So we have the same endpoints of the same graph happening here. So they already gave us this. This is given. We're going to pick that up and run with it. So we know that x equals 4 minus y squared. Well, in that case, it's going to be easier to let y be our parameter. So we're going to let y be the parameter. Then x equals 4 minus y squared, and y equals y. And our bounds are, if you look at the graph, we're going to go from negative 3 to 2. So y is bounded from negative 3 to 2. Oh, how do you know when you use t and when you use something else? Well, they're already related here, so you can go ahead and pick them up and use them in that way. And that's when it's going to be nice to use x or y instead of using t and switching variables. It just takes practice. As with all of calculus, it just takes practice. Now, also, good math habits make good math students. So let's build the habit of finding the derivative right now. Now, since our parameter is y, we're finding the derivative with respect to y. So dx is going to be negative 2y with respect to y. And dy is just going to be equal to dy, so that's not bad. So now we can integrate, and our bounds for y are negative 3 to 2. And, oh, well, let's write the problem down before we do that, because I don't think I have it anywhere here. So I have the integral over c And the problem says y squared dx plus x dy. Okay, now we can say the integral from -2 to 3, and y is just y, and we're going to square it, times dx, which is -2 dy, plus x, which is 4 minus y squared, times dy, which stays dy. So now we have -3 to 2, and here we have -2y to the third with respect to y, plus 4 minus y squared with respect to y. So we have -3 to 2. And let's combine our like terms to be one nice pretty polynomial. So we have 2y to the third minus y squared plus 4 with respect to y. So we can integrate this, and we have -3 to 2. Oh, we're going to integrate, so let's leave that off. So when we integrate, we have -2 over 4. So we have -1/2 y to the fourth minus 1/3 y to the third plus 4y, and we're integrating from -3 to 2. So when we put in 2 to the fourth is 16 divided by 2 is 8, -8, minus 8 over 3, plus 8, oh that's pretty, minus 3 to the fourth is 81, so we have -81 over 2, minus 3 to the third is 27, divided by 3 is 9, but two negatives make a positive, and minus 12. So now we have -8/3 here, and we have plus 81 over 2. And 9 minus 12 makes a -3, but there's a minus out there, so that becomes a plus 3. And when we look at that, we can use your handy-dandy calculator if you'd like, and we get 245 over 6. So this is C2. So remember, for C1, we had -5 over 6, and for C2, we had 245 over 6. Now, we looked at the same, we had the same problem. Both of the problems said the integral over the curve of y squared dx plus x dy. And we don't use parentheses around that because it gets very complicated, messy. I'm a stickler for notation, so I believe they should have parentheses, but it's common to leave them off and know that that integral applies to the whole thing. But what I want you to see is we have two different values here, because if you go back to the graph, the curve that we used for our bounds for our integral is very different. So we have two very different answers here. So in general, the value of the line integral depends not just on the endpoints of the curve, but also on the path. Notice they have the same endpoints. So the longer path obviously gave us a bigger answer. So it's important. Notice also that the answers in example 4 depend upon the direction or the orientation. So both of these are going up. So your answer should be positive, but if we were going down, your answer would be negative. So in general, given the parameterization determines the orientation of the curve, and so you have to be careful to that. So this problem says to integrate over the curve, and we're integrating x to the 8th y plus sine x with respect to y. Now this is a line integral because instead of given the bounds like 3 to 5, we're given a curve as our bounds. And the curve is the parabola y equals x squared from 0, 0 to pi, pi squared. This is another one where we're not going to want to work in terms of t. So let's look at the fact that we have y equals x squared. So let's let x be our parameter. And when I write that out, it helps me think about what I'm integrating with respect to and what I'm writing for my equations and things like that. So let's let x be our parameter. Then x equals x and y equals x squared as we have here. And notice x is bounded between 0 and pi. And then our good habits, good math habits, make good math students. So dx equals dx. And our derivative of y with respect to x is 2x with respect to x. So now we can go ahead and do our integral. Let's take our given integral up here. So we have the integral over c of x to the 8th y plus sine x dy. And we've used all the stuff about c, so let's move this up. So we're going to say that this means the integral, and x is equal to x, so we keep x to the 8th, times y, which is x squared, plus sine of x stays x, and dy is 2x dx. In this case, we didn't need dx The last problem actually had something dx plus something dy, so we needed both of them. So we're going to say this is x to the 10th times 2x makes 2x to the 11th plus 2x sine x dx. Now I'm going to split these into two integrals because when you integrate this, first one you get 2 over 12, which is 1 over 6 x to the 12th, plus the integral of 2x sine x dx. And I forgot to put bounds on, so let's go back. Our bounds from x are 0 to pi. So we should have put 0 to pi in each of these lines. I apologize for that. So this is 0 to pi. Let's go ahead and finish that one. So we have 1 over 6 times pi to the 12th. And x is 0 means it's gone. So we have plus the integral from 0 to pi of 2x sine x dx. Now this requires integration by parts, and you should not be doing integration by parts in your head. So we have u. So our u is going to be 2x, and the derivative of that is x. I'm sorry, it's not x, it's 2 dx. And then dv is everything else, which is sine x dx. And the antiderivative of sine is negative cosine of x plus c. So I'm going to say the plus, and I'm going to wait and bring down that 1/6 pi over 12 at the end. So we take uv, which is 2x times negative cosine x. I'm going to say negative 2x cosine x from 0 to pi. And then we have minus the integral of 2 times negative cosine x, that is negative 2 cosine x dx. And the bounds still are 0 to pi. So we have, let's take that plus out and put a minus there. We have minus 2x cosine x from 0 to pi plus 2, and the antiderivative of cosine x is sine x from 0 to pi. So we have negative 2 pi, and cosine of pi is negative 1, plus 2 times 0, so we're just going to put a 0 here, plus 2 sine of pi. Sine of pi is 0, and sine of 0 is 0. Oh, these are both minuses. I knew there were zeros, so I didn't think about the signs, but you should do good math at all times. So this is minus 0, minus 0. Doesn't really matter. Now, remember out front, up here, we have 1/6 pi over 12. So we have 1/6 pi to the 12th. So we have 1/6 pi to the 12th plus 2 pi. And that's our answer for this line integral. So suppose you have C, a smooth space curve, given by parametric equations x equals x of t, y equals y of t. We say t, but we know it doesn't have to be t, and z equals z of t. So we've moved into space of 3D graphs and curves. So we have t is bounded by a and b. So when we do this, we have, we're in 3 space. It could be bounded by a vector equation. So it could be r equals x of t, y of t, z of t. Let's say or here, because it's not going to be both. So if f is a function of 3 variables and it's continuous, then the line integral is defined as the integral over c of f of x, y, z with respect to s is equal to the integral from a to b. Now that's your terms of t. And you have f of x of t. I hate this notation. It gets so complicated here. But you have x, y, z in terms of t. Do you see this? X, y, z in terms of t. And then we have the arc length for 3 space. So we have dx over dt quantity squared plus dy over dt quantity squared plus dz over dt quantity squared with respect to t. So you're doing the same thing, we're just moving into a 3 space. So if you look at the fact that you can use vector notation here, we could say that this is equal to the integral from a to b, And we can call this f of rt, where r is our vector. See how much prettier that is? It's definitely true. And we have the square root of x, the derivative squared, which is the length of r prime of t with respect to t. So this is our nice handy notation, one of these two. And just like we did before, sometimes we have more than one variable. So we could say that the integral over c could be written as p of xyz dx plus q of xyz dy plus r of xyz dz. So that's where you put more than one variable into an equation. So let's look at one of these. All right, evaluate the integral of c sine z ds, where c is the circular helix given by x equals cosine t, y equals sine t, z equals t. The bounds are from 0 to 2t. I love when they set everything up for you. Don't you love that? It's always so nice. Makes me want to say thank you. That's so sweet. So let's look at the integral over c of y sine z ds. Now, we know that x equals cosine of t, and y equals sine of t, and z equals t. So your next step is your differentiation. So the derivative of cosine is negative sine of t dt. The derivative of y is cosine of t dt. And the derivative of z is just dt. The derivative of t is 1. So we can set up this integral and say the integral, the bounds of t are given to be 0 to 2 pi. And we have y, which is sine of t, times sine of z, which is t, and then ds. ds is the square root. I'm going to need a long square root, so I'm going to kill the picture for a minute. And we're going to say the derivative of x is sine of t squared. I'm going to go ahead and square it and call it cosine of t squared, plus the derivative of y is cosine and sine squared, plus the derivative of z is 1 squared, and then we have with respect to t. So we have the integral from 0 to 2 pi, and here we have sine squared t, and we have the square root of cosine squared plus sine squared is 1, so we have the square root of 2 dt. Now that's a nice constant, so we can pull that out, square root of 2, the integral from 0 to 2 pi. Now you cannot integrate sine squared as it's written. You have to use an identity. So we're going to use 1/2 times 1 minus cosine 2t. That is the correct identity to use in this case. And we're going to integrate with respect to t. Now I'm going to use u sub. Some of you skip those steps, but when I do, I always make a mistake. So I'm going to let u equal 2t. So du equals 2 dt. So dt equals 1/2 du. And then we need to change bounds. So when x equals 2 pi, t equals 4 pi. When x equals 0, t equals 0. So we have, let's pull this 1/2 out here. So we have square root of 2 over 2, and our bounds are 0 to 4 pi. And now we have parentheses 1 minus cosine of u times 1/2 du. Now we can pull this 1/2 out as well. So we have the square root of 2 over 4. And when we integrate 1 with respect to u, we get u minus sine of u from 0 to 4 pi. That's going to be pretty. So we have the square root of 2 over 4. And we have 4 pi minus 0 for u, minus sine of 4 pi is 0, minus sine of 0 is 0. So we end up with the square root of 2 times pi. It's such a pretty answer. I love when they give you everything at the beginning to set it all up. Isn't that fantastic? So good. All right. So evaluate this integral where c consists of line segment C1 from those 2 points to the vertical line segment C2 from those 2 points. So when we get done, we're going to add those. Now notice C2 is going down, so it should have a negative value, and C1 is going up, so it should have a positive value. And we have the endpoints that were given. So let's start off with C1, and we need the parametric equation. And if you think about the fact that you're going from these values, we built it this way. So we said that x equals, the difference between the x's is positive 1. So we're going to say 1t plus 2. You could pick either point, but I'm going to pick the first point. Y equals 4 minus 0 is 4t plus 0, and z equals 5t plus 0. And t is between 0 and 1. Now, when we do this, our next step is to find the derivatives. So dx equals, with respect to t, because we have t's everywhere, so t is my obvious parameter, so I'm going to say dx equals dt. And then dy equals 4 dt, and dz equals 5 dt. Now we're going to say the integral over the space c of y, the space c, our bounds are in terms of t from 0 to 1, and then we have y dx. So y is 4t, and dx is just dt, plus z, which is 5t, times dy, which is 4 dt, plus x, which is t plus 2, times dz, which is 5 dt. So we have the integral from 0 to 1, 4t dt, plus 20t dt, plus t plus 2. Nope, we're multiplying by 5. So we're going to call that 5t plus 10 dt. And then let's make it 1. Let's combine like terms. Don't do extra work. Combining like terms is easy. So if you had 5t and 20t and 4t, that makes 29t. So we have 29t plus 10, and then we're going to integrate with respect to t. So when we integrate, we get 29 over 2, t squared, plus 10t from 0 to 1. So when we plug in 1, we get 29 over 2 plus 10, makes it 49 over 2. That's our C1. Now we need to find C2. I'm not sure if I want to bring the equation back or the picture back. I think I'll bring the picture back. So I'm going to build this the way we did earlier in the class. We're going to say x equals, the difference is 3, so the difference of 3 minus 3 is 0. So I'm not going to put a t, and I'm going to use this first point here. So I'm going to say 3, and then y equals 4 minus 4 is the slope of 0. So we're going to use the value of 4, and z equals 0 minus 5 is negative 5t plus the y value of 5. And t is between 0 and 1. I'm going to move off to the side. I'm going to move it this way. And I'm going to say if we use the formula they gave us, because some of you are formula people. So if we use the r of t equals r 1 minus t times r of o plus t times r of r sub 1. Now then your initial one is the starting one with the arrow on it, so 3, 4, 5. So you would say r of t equals 1 minus t times 3, 4, 5 plus the second point, which is t times the second point, which is 3, 4, 0. And you'll find that r of t equals 3t, 3 minus 3t plus the 3t below, 4 minus 4t plus the 4t below, and 5 minus 5t. So if you simplify these, you have the t's cancel and you have 3, the t terms cancel and you have 4, and you have 5 minus 5t. So that's where you get your x, y, and z equations. So if you want to do it that way, you may. It's a formula and you have to memorize, and so I'm not a super big fan of that. So now let's do our next step, which is our dx. Our dx is 0, and our dy is 0, and our dz is negative 5 dt. All right, so let's go ahead and go back to our equation. Our equation says the integral over c of y dx plus z dy plus x dz. So the integral in terms of t is 0 to 1, and y is 4, but dx is 0. So this is 0. Plus z is all that stuff, but dy is 0. Plus x, which is 3, times dz, which is negative 5 dt. So we really only have the integral from 0 to 1 of negative 15 dt. So we integrate that, we get negative 15t from 0 to 1. And when you plug that in, you get negative 15 minus 0 is negative 15. So this is c2. So in order to find our total line integral, we have to add c1 plus c2. And c1 is 49 over 5 minus, 49 over 2 minus c2 is 15. That's why I went ahead and put the minus. That's 30 over 2, so we end up with 19 over 2 for our line integral. That's not too bad. When you're working in 3-space, you're just going to work in 3-space. But it doesn't get very much more difficult. So this chapter is vector calculus, so we are going to head into vectors. So if we think about work that we learned back in Calc 2, so the work done by a variable force is done by an integral where the work is the integral from a to b of f of x dx. So we've done a lot with work. I have a picture for you here of a vector field. It's a very specific vector field. We're actually going to work with it in a minute. But before we do, let's talk about the line integrals of vector fields. So if you look at this box, it says, let f be a continuous vector field defined on a smooth curve C given by the vector function r of t, where t is defined between a and b. Then the line integral of f is the integral of f with the dot product of dr. So this is the integral from a to b of f of rt times the derivative of rt dt, and it can be written as the integral of f and the dot product of t. So the one in the middle is helpful. The one on the end can be helpful. You just have to decide what's helpful for you. We're going to use the one in the middle the most. So this is the one we're going to pick up here. Let me pick a different color so you can see. This is the one we're going to pick up most of the time here. So remember that f of rt is just an abbreviation for this vector field. And we simply use these equations in that expression for f of x, y, z. And dr is the derivative of r with respect to t. So we're not really changing what we're doing. We're just looking at it written a slightly different way using vectors instead of just equations. So let's look at an example on that. Before we look at an example, let's go back to this vector field. So let me tell you, if you look at this vector field, it's a force field curve. And if you look at it, it's the answer is going to be negative. The answer to the integral is negative because the movement is going down. So the field, it literally says the field impedes movement along the curve. But I didn't give you any problems that involve the concept of work, so I'm not going to do that. We're just going to move on to one more. Well, maybe one more, maybe more than one more. So we have our x, y, and z defined up here, but let's go ahead and put these things in terms of r. So we know that our vector r is x, y, z. So we have t squared, t to the third. And then r prime is going to be equal to 1, 2t, 3t squared. And then f in terms of r. So f is xy, so x is t and y is t squared, so that's going to be t to the third. And y is, the second component is yz, so t squared t to the third is t to the fifth. And then the last component is zk, zx, which is t to the third times t, which is t to the fourth. So now we're going to do the integral with respect to c, or over the curve z, of f dot dr. Now dr, we can rewrite dr to say the integral over c of f times r prime of t with respect to t. So keep in mind that that's going to be a normal notation that we can use there. Remember, I told you that's the notation we're going to like, but remember this is a dot product. So we're going to say the integral in terms of t is 0 to 1. And we have f, which is t to the third, t to the fifth, t to the fourth. And we have the dot product with r prime, which is 1, 2t, 3t squared. And we're going to put all of this, integrate with respect to t when we're done. So 0 to 1. Now when we do a dot product, we have t to the third times 1 is t to the third, plus t to the fifth times 2t is 2t to the sixth, plus t to the fourth times 3t squared makes 3t to the sixth with respect to t. So we have 0 to 1. And I'm going to combine like terms. We have t to the third plus 2 plus 3 is 5t to the sixth dt. So when we integrate, we have 1/4 t to the fourth plus 5 over 7 t to the seventh from 0 to 1. So this means we have 1/4 plus 5 over 7, which gives us 27 over 28. Now, that's our line integral. Let's look at one more thing. So finally, look at the connection between the line integrals of vector fields and the line integrals of scalar fields. So suppose the vector f, the vector field f on R3 has component form f is equal to pi plus qj plus rk. Then when you compute the line integral, you get that craziness there. Pause and think about it. But this is exactly like the line integral in 10. Therefore, we can say that this integral here is equal to this mess where f is a component. So the one that we did in example 6 could have been written in that way. It's just another way to write it, but it'll make sense as you do it. Example 6 is the one we did with the two line segments for C1 and C2, and one of them was positive, one of them was negative. So we could have worked it out that way, but what we did is fine. You could go either way, and I hope that you enjoyed this lesson and have a great day.